So our first task today is going to be to kind of reiterate sort of some of the stuff that we did last week. We're going to reconstruct a new surface, then we're going to work off of that surface in all three axes, right? So the U and V axes across the surface and the normal direction off of the surface, basically. So in order to do this, I'm going to just kind of create an interesting sort of surface for us to work off of. So what we did before was to just create an arc and then extrude it upwards, right? And that largely created a straight vertical but curved surface for us to work off of. And that's what the assignment that you were given at the end of last week was based on. And so now we're going to start to develop an understanding of warped surfaces and what that means for what we can and can't create. So the first iteration of what I'm going to do here is to just look at the subdivisions of a warped surface and try to understand what the challenges are going to be. So in order to do that, I'm going to start off with just two splines. We're going to just kind of make two competing S's in the top view. It doesn't have to be anything super accurate. I'm just going to kind of do something like that and then create one that goes the opposite direction, a little bit like this. And ultimately, it doesn't really matter how far you pull it up, but just grab one and pull it up like this. And those two surfaces are going to be lofted together. So enter the loft command, select them both, and hit enter. Your loft options, don't worry, the defaults should be fine. So under display, I'll put this on here so you can see. And just try to get yourself to a position where you have this, wet piece of paper sort of thing going on here. Okay, so I'll give you guys a minute or two to get caught up with that before we move on to actually subdividing it. All right, so moving forward then, some of you probably already started moving toward subdividing it, but I'm going to use the similar exercise from what we did before, subdivide it, try to loft the two edges together so that I can get flat panels, and we'll see what the challenges are. So the first thing I need to do is first reference the surface and then use my divide domain squared with a ISO trim in order to subdivide it. So this is kind of like the golden triangle here. I keep saying that. So under params, geometry, and surface, just right click that and set one surface and go to this. And for ease of viewing, I'm going to go back into Rhino and just turn that layer off. So it's kind of a clear red surface. Then I'm going to go to math, domain, divide domain squared. And I'm kind of moving through this faster than I normally would because you've seen this now 2 or 3 times. So you should be able to follow along a little faster. So that's under math and domain. And I'm going to go to surface and utility to find isotrim, which is otherwise known as subdivide surface. Remember that. So this surface plugs into the I input domain for the subdivision. It also plugs into the surface input of subdivide surface, and then the divided surface gets plugged into the domain input of subdivide surface. And you'll see those subdivisions appear over here, right there. And of course, I'm going to modify them to something that's a little bit more curtain wall-like, so we can study it in an architectural application here. And I'll go to 0 is less than 10. Plug them both in and just put a couple subdivisions in each direction. In fact, I'm only going to do, actually, since I kind of have a long linear one, I'm only going to do one U-count subdivision. And I'm going to do 6 V counts so that I basically just get a bunch of vertical panes, right? So these are kind of going to be my glass panes, so to speak. And then you guys are keeping up with me so far? Now that you've done it a couple times? All right, so I'm going to keep moving then. What I'm going to do from here is deconstruct, right? Remember, we constructed the geometry. We're going to deconstruct the geometry and then reconstruct it into something else. So first and foremost, I'm going to make an assumption here that says this absolutely must be my surface, right? Imagine that you're in class, your design is done, and this is the design, and you need to make it a panelized surface. Okay, so imagine that's the case as we go through this. So I have to deconstruct it. And remember, I'm trying to make flat panels like it's glass. Okay, deconstruct under surface analysis. Deconstruct BREP. And then remember, what did we use to isolate one edge and another edge? Do you remember? The left and right edges. List item, yeah. Very good. So under set and list, we used list item. And we used that to grab edges. And making a slider from 0 to 3 because it's quadrilateral. Plug that in here, and it looks like the 0 index is giving me the panel edge on the left side of the panel. And then if I copy those two down, and then slide over here and try to figure out that one, number 1 is at the top, and number 2 is on the right side of my panels, since the left side is not selected. All right, and do you guys recall off the top of your head what command we used to connect these panels?
Ruled surface.
Ruled surface, yes, very good. Man, you guys are quick. So under surface and freeform, we used ruled surface. So this is creating a surface between two curves, and this one gives us the option to connect an A and a B. So this is the list item here and the list item there, which gives us, well, it's a reversed surface. So if you have trouble viewing it, turn your old stuff off, and this is what it gave you, which is not correct. So if you recall from last week, what was the issue that we have? Anyone remember? No. Very close though. Well, sort of close.
To make sure they're facing the same way?
Yes, very good. Yeah, so we have to reverse one of the curves because the direction of these two curves are going opposite directions. So when it connects them with a surface, it flips it over so that the direction of that curve matches. So we can go to, let me mark this for you. Surface freeform, and we can go up to curve, and I believe it was in utility. Flip curve is what we want. So it doesn't really matter which one. You're going to get your normals on one or the other side depending on which one you flip. So I'm just going to flip the first one up here. So I'm going to put the curve in the curve input and then take the flipped curve output and plug that in there. So what we get, let's look at it in the top view. What we get now are straight edges at the top and the bottom. However, going back to going back to perspective now, what you can see, if you can follow this, is that while you do have a straight edge on all four sides, because those lines are skewed, you have a warped surface still for each of the panels. So it's kind of a step in the right direction, but it's not technically correct. Okay, so if this is the surface that I absolutely want to use, what do I have to do to the surface to make it work? Does anyone know?
Divide it.
I have warped surfaces. Okay, divide it. Divide it how? How would you divide it to make this work? Anybody? All right, that's right. I'll walk you to it. So when you have warped surfaces, let's assume your outer boundaries are exactly where they need to be. The only way that you can panelize and make warped surfaces, right, quadrilateral warped surfaces, right, so four straight edges that are skewed, is to triangulate them. You have to triangulate it. It's the only way you're going to get flat planes. Otherwise, you have to look at ways of moving the matrices, right, like the point matrix, so that it creates your quad panels to be flat, essentially. Okay? So those are your sort of two options in terms of design and what you need to do here. Okay, so assuming this is exactly what I need, but I need flat panels with it, I need to triangulate it. So we're going to do that in the next video. Are there any questions about what we've done so far? Okay.